Part one of this project is to find the elastic modulus of the aluminum and the steel. To find the elastic modulus, we would take the material's stress and divide it by the strain. Or in other words, you could take the force per unit area of the material and divide it by the ratio of change that the material undergoes. You could also look at the stress strain graph and use the slope of that graph to find the elastic modulus. So for aluminum, we found that our elastic modulus is 1,354. And for our steel, our elastic modulus was 1,520.3.
I'm going to show how to calculate Young's module or elastic modulus for gold, which is our third chosen material. Using the previous example, which was stainless steel, we can see that already this is a completely straight line, and this is not. So where is the yield point? Where is the limit between the elastic and the plastic region? Here we can tell this is an E, this is the point where this is elastic and the rest is plastic. Here we're better off using the slope method, which is this one. It consists of picking 2 points in the strain line, like so, one here, for example. You just intersect them with the curve, and then you'll get 2 other values for stress. So using again the formula, we'll just put them there, and then we'll divide, and that will give us Young's module. I'm gonna cover the second point of the first project of this course, which is Material Science ESC 220. So let's start with. The question was, how do we find the yield point and the yield strength? Well, it's quite simple. The yield point, it's nothing but the limit or the intersection, I could say, where the elastic stress curve meets the plastic stress curve. For example, this is the lab results for group 12. This is steel, and here we can see the stress strain curve. Here, as we can see, it's very linear up until this point where it bends. This exact point is the yield point, and due to how the material behaved, this is also called a knee, which is a very sharp bend that let us know just that the plastic curve, the plastic deformation starts here. Now, how do we calculate yield strength? Or it's not really complicated. We just need to use the offset method, which consists on applying on the strain curve, on the strain line. We will do 0.002, all right, and then do a parallel line with the linear or elastic region of the material, and wherever it intersects, which should be around here, 175 megapascals, that's our yield strength.
As shown on the graph right here, the yield strength for gold is 120 megapascals compared to the stainless steel, which is going to be 860. So we'd be better off using steel than gold.
Tensile strength is found by dividing the tension force by the original cross-sectional area. Tension force is demonstrated by Ft, while original cross-sectional area is demonstrated by A0. I have done 2 examples using aluminum and steel to demonstrate how to find the tensile strength. In the aluminum, I had to convert the force into newtons as it was in kilonewtons. Then I divided to get 215,028,571 pascals. For the steel, I also had to convert into newtons, as that was also in kilonewtons. I then proceeded to divide to get 1.09 times 10 to the 9th power pascals. I also have demonstrated two graphs. In the steel graph, it broke at 22,914.9 newtons of force, while the aluminum broke at 4,515.6 newtons of force. This demonstrates that steel needed a lot more force to break.
This is part 4 of Project 1 for Material Science. In this part, I'll be going over percent elongation and percent reductional area. The formulas are shown on the screen. Percent reduction of area is equal to area of original cross-section minus minimal final area all over area of original cross-section multiplied by 100. And percent elongation is equal to final length minus original length all over original length multiplied by 100. These are different materials that we've tested in the lab, and the gold is a chosen material by us. So the higher the percentage, it will undergo significant deformation before it fractures. The first equation is the original cross-sectional area, which equals to pi, original diameter, all over 4. And then next one is final cross-sectional area after deformation, pi, final diameter at fracture over 4. And the percentage is shown on the screen. For elongation, softer materials stretch more, which will cause higher ductility. So the first equation is the change of length, which equals final gauge length after fracture minus the original gauge length. And then you'll see that the numbers change because gold is a much softer and frail material than aluminum and steel.
Question number 5 asks us to find the resilience of our materials. Resilience can be defined as the energy a material can absorb before plastic deformation. Now, we can see on a typical stress versus strain graph that resilience is going to be the area under the linear part of our graph. But now what if we wanted to find numerical values for this? Well, to find the resilience, we're going to take yield strength squared and divide it by 2 times the modulus of elasticity. We have another option for an equation, and this is going to be yield strength times yield strain over 2. Now let's carry on with doing a real-life example. For this example, we're going to be using gold, as our numbers for steel and aluminum seemed a bit off for this example. But nonetheless, we're going to continue on. So, to my left, you're going to see that I've already plugged in the yield strength and modulus of elasticity converted to pascals for ease of calculation. So we're going to have on the top 1.2 times 10 to the 8 squared over 2 times 7.5 times 10 to the 10. So once we carry out the squaring on the top, we're going to get 1.44 times 10 to the 16, and on the bottom, we're going to get 1.5 times 10 to the 11. So now once you carry out the division, we're going to end up with a resilience of 96,000 joules per meter cubed.
Part 6 of this project is to find the toughness of the 2 materials that we use. Toughness is the amount of energy that the material can take before it breaks. And to solve for the toughness and to find an approximate value, we must take the area underneath the stress-strain curve and evaluate it at 0 to the yield point, which is where the material broke. And you have to integrate it with respect to strain. So taking the slopes of the 2 graphs we were given for steel and aluminum, I found that the toughness for aluminum to be 2,520 joules per meter cubed, And for steel, I found the toughness to be 6,313.83 joules per cubic meter.
In the video of Spider-Man attempting to stop a boat from continuing to split in half, it is demonstrated that force can overcome tensile strength, causing the material to snap in half. In the video, this is demonstrated as Spider-Man's spider webs are split in half over the force of the boat falling. The force was pulling outward and was falling down at an angle, which caused the webs to be pulled right in half.